Hello everyone, the goal for this video is to take a closer look at some of these physical quantities that are represented by vectors. Starting with position. If you want to describe an object's position in 2 or 3-dimensional space using a vector, then the convention is this. The vector, if drawn with its tail at the origin, very literally points to the object's position. So you're in whatever frame of reference, you have a notion of which directions represent positive x, positive y, if you're in 2-dimensional space, or if you're in 3-dimensional space, you might have a frame of reference with 3 coordinate axes. You have in your physical problem decided where is the origin, and you want to indicate some location. Let's say it's up here marked with this blue x, over here marked with this blue x. The vector corresponding to that position would simply be the one which, if you decided to draw it from the origin, would point to that object's position. So this blue vector is the example in 2-dimensional space, and this blue vector would be the example in 3-dimensional space. In this case, what does the length of the vector represent? The length of the vector represents the distance between the point and the origin. What does the direction of the vector represent? It simply represents the direction that you'd need to travel to get from the origin to the position along a straight line. Next up, velocity. For an object that is moving in 2 or 3-dimensional space, we speak about its velocity in terms of a vector. What does the direction of this velocity vector represent? The direction represents the direction of movement. Meanwhile, the length of the vector represents how fast the object is traveling, the speed of the movement. So for example, suppose that you had an object in 2-dimensional space who was moving along a circular track. I take an instant in time and freeze it, and look at the object's position at that moment. At this instant in time, which direction is the object traveling? It is traveling for that short moment straight upward. And the length of that green vector that I draw straight upward to capture the direction of movement at that instant, the length of that vector would capture the object's speed. So velocity. Velocity vector tells you how fast the object is moving and in what direction the object is moving. Now, if your position is 2-dimensional and your velocity is 2-dimensional, then your acceleration will be 2-dimensional also. And likewise in 3D. If your position is 3D, your velocity will be 3D, and your acceleration will be 3-dimensional as well. The direction of acceleration is somewhere between the direction of movement and the direction of turning. For example, if you had an object that was moving on a circular track, then the direction of movement at this instant is indicated here in yellow. At that instant, it's moving straight up. And the direction of turning, it's turning to the left at that instant. So the direction of turning would be indicated in green here. The acceleration vector is going to live somewhere between those two directions. So it's plausible, for example, that the acceleration vector could be here in red, directly between the direction of movement, the direction of the velocity vector, and this green vector in which this object is turning. Now, where exactly between the direction of movement and the direction of turning does the acceleration vector lie? Well, it's different depending on what exact scenario you're working in. And we're going to go into that in more detail when we get to our video on tangential and normal components of acceleration. That's what's going to tell you how far this acceleration vector is angled toward the yellow vector versus this green vector. Now, the magnitude of acceleration also has a sort of dual nature to it. The length of the acceleration vector captures how your velocity is changing. But because velocity has two components, direction of movement and speed of movement, acceleration has two components as well. The length of the acceleration will in some new sense capture the change in the object's speed, how fast it is either accelerating or decelerating in the forward or backward directions, and it will also capture how quickly this object is turning. Once again, more on that later. The next physical quantity that we can represent using a vector is a quantity called displacement. Displacement is straight line movement from one point to another point. So for example, if I had a position in two-dimensional space indicated by this green dot, and I had another location in two-dimensional space indicated by this green dot, then I could draw a vector between them. And this blue vector would represent the displacement from point A to point B. In this context, the direction of the vector represents the direction that you would have to travel to get from point A to point B. And the length of this displacement vector would represent the straight line distance from one point to the other. No detours. If you headed straight from point A to point B, what would be the distance between those two locations? Displacement. The next physical quantity that is represented using by vectors is a force. A force vector represents something that is acting on an object that is causing its movement to change, something that is acting on an object that's causing it to accelerate. The exact relationship between the force applied to a vector and the acceleration that results from that force is given by Newton's laws, which says that if you take the force that is applied to an object that has a mass of m kilograms, then the force will be equal to the mass times the acceleration. Now, in this context, What does the direction of the force vector represent physically? It represents the direction along which the force is applied. If you push on an object straight down, then the force vector would point straight down to capture that. What does the length/magnitude of your force vector represent? It represents how strong the force is. In physics, the magnitude of the force. Now, there are a couple of special forces which are usually given special attention, and one of the most famous forces of all is gravity. Now, if you're dealing with any two objects at all, whether it be you and planet Earth and the moon, the sun and the earth, or even some objects so small as maybe your coffee cup and the pencil next to your coffee cup, anytime you have any two objects at all, they are both exerting gravitational force on each other. The only thing is that when the objects are pretty small, like your coffee cup, like yourself, the gravitational force is so small that we usually don't notice it. So if you're looking at the gravitational force exerted by a body A on a body B, then the gravitational force is going to have the following properties. First of all, the direction of the force is going to pull object B in toward object A. So the direction of gravitational force applied to object B points in toward object A. The second property, the magnitude of gravitational force depends on both the size of object A if you have, for example, a large planet, it's going to exert more gravitational force than a small moon. It also depends on the mass of the object that's being acted upon. For example, when you're on planet Earth, the quantity that captures the way that gravitational force acts on a person is what we call the person's weight. So a person that has a larger weight is having more gravitational force act upon them than someone that has a smaller weight. So the magnitude of gravitational force depends both on the object that is exerting the force and on the object that's having its force that is being exerted upon. And it also depends on the distance between them. There are some very, very, very large objects in our galaxy, in our universe. But as they are very far away from us, the gravitational force that they affect us with is very, very small. Whereas the Earth, for example, or even the Sun are relatively nearby. So things like that are exerting a much greater gravitational force upon us. Now, in the specific case of the gravitational force exerted by planet Earth on those of us who are close to the Earth's crust, the Earth's surface, sea level, in such a situation, the magnitude is equal to the following quantity. The mass of the object that's being acted upon multiplied by this number, 9.81. This number here, nicknamed lowercase g, is referred to as the acceleration due to gravity. The direction of gravitational force is also well understood. The gravitational force exerted by the Earth will always pull us, as we understand it, down toward the ground, down toward the center of the Earth. Now, within the context of this class, if I refer to an object that's being acted upon by gravity, I am going to be referring to Earth's gravity unless otherwise stated. The next force that we're going to have a slightly closer look at in the context of this class is friction. And one of the really interesting things about friction force is that the direction in which it's applied is always opposite the direction of movement. So if, for example, I have an object whose movement is this way, whose velocity vector is, say, to the right, then I know right away that the friction force will have to point to the left. Friction acts to impede an object's movement. Now, the length, the magnitude, the strength of friction force depends on a lot of different variables. If you're dealing with a surface or with an object that's really slick, then your friction force is going to have a low magnitude. But if you're dealing with an object that's really tacky or coarse, that's really going to work hard to slow down objects, then your friction force is going to have a large magnitude.